So, guys, welcome to the post-contest discussion of the Codechef Starters 141. And I'm Abhinav, and this is TLE Eliminators. So, let's get started with the first problem. Okay, so, we are going to look for the div 2, the first problem of div 2, which is a redundant array. So, Ceph has an array A containing n integers. He can perform the following operation on the array as many times as he likes. So, choose an integers L and R such that L and R lie in the range of 1 to n. Choose a positive integer x, and for every index from L to R, inclusive both, set ai to x. Now, the cost of such an operation is R minus L plus 1 times x. Find the minimum cost required to make all the elements of A equal. So basically, we are given an array, and then we are given a type of operation. So in one operation, what we can do, we can select a range from L to R, and for the full range with both L and R inclusive, we can assign a positive integer x to each element in that range, and the cost for that operation is the size of the range. L minus R plus 1 is the length of that range multiplied by x. So that's the cost of the operation. And then we have to find, like, we can apply this operation many times, but it would take this cost every time. So find the minimum cost required to make all the elements of A equal. That's why our target. Whatever we have to make all the elements of A equal. Okay, with minimum number of operations. So now what can we do here? Okay, so let's take the first test case. So what we are given, that we are just given an array A. Okay. And we are asked to find minimum number of operations to make all the elements of this array equal. That's our target. Okay. So in operations, if you see what we are given, we have to choose L and R. And then for the range from L to R, for this full range, we have to assign AI equal to X. We have to choose L, R, and an integer X. So, and the cost of this would be R minus L plus 1 times X, which is length of the range into X. So basically, if let's say we choose this range, okay, we'll just choose a subarray from this array, any range from L to R. Let's say we choose this range of length 3. So we can just choose this range and assign some value to the whole range. So we can make, if we choose X equal to 2, we can make all the three elements 2, 2, 2 after one operation. And the cost of this would be length of the range. R minus L plus 1 is the length of the range into X. Okay. So if you like see, if let's say we are applying for this range, okay, if we take 0 based indexing here, in the question it was given 1 based indexing, but we can take 0 also. There is no problem. Just L and R would decrease by 1. It won't affect anything. Okay. You can take with 1 based indexing also. It doesn't matter. Now what we can do, let's say we picked L equal to 1, R equal to 3. This represents our range from 1 to 3. And then let's say we picked X equal to 2. So what would happen for this range? All the elements would become 2, 2, 2. That's what is going to happen. So let's say we made all the elements 2, 2, and 2. Okay, and the cost of this operation is the length of the range. So 3 minus 1 plus 1, R minus L plus 1. What is this? This is 2, 3. This is 3. So there are 3 elements in this range. So this is actually the length of the range, whatever we chose, multiplied by X. X was 2 years, so it would be into 2 years. So 3 into 2 is 6. So basically what we are doing, the length of the range into X means for every element that we change, we require a cost of X. So for every element that we change, we require a cost of X. So instead of giving the operation as L to R, we can change the whole L to R to X. If it would have been given, just pick an index I and change AI to X. This, if the question was this, then also the problem would be exactly the same. Like if we are doing from L to R range, what we are doing, we are basically assigning every integer from L to R as X. So if we are doing from this range of 3 elements, we can do it 3 times for each element. We can just pick a range from this 1 to 1, that is a single element, make it x. Then pick this range, make it x. Pick this range, make. What cost would it cost? It would also cost x plus x cost only. And if we are doing it in a single time, still it would cost 3x. So what I'm telling, instead of considering is as making a range from L to R as X, we can consider it as making picking up any element and making it X. That's what we can consider the operation as. Now, if we consider it like that, then what we need to do? We need to make the all array elements equal. So how can we do it in minimum operations? So if we had 2, 4, 3, 2, 2, this was our array. So what can we do? To one way is just make all the elements equal to x. Just pick any x. Just maybe you pick x equal to 5. Make all the elements 5. So in that way, we can always make all the elements equal. But what cost would it take? It would take the cost of whatever x we are picking multiplied by there are n elements. So it would take x into n cost. But instead of choosing some x which is not in the array and changing every element, to minimize the cost, we would try and pick such a value which is there in the array. So let's say we picked 2. Okay. So we can maybe pick 2 and then make all the elements 2. And wherever we already had 2, we don't need to change that. So we won't waste a x cost in that. So if we are picking x equal to 2, that is we are making all the elements equal to 2, then we would only apply the operation on the elements which are not 2. So we will apply the operation on this 4, make it 2. So it would cost an cost of x. X is 2 here, so 2. Now make this 3 as 2, it would cost a cost of 2. Now these are already 2. So in total, we had a cost of 2 plus 2 equal to 4. In a cost of 4, we were able to make this array as all elements equal. So this was one way. Or another way was if we pick x equal to 3, then 2, 4, 3, 2, 2. What we could have done? This 2 is not 3, so we would change it to 3 with a cost of 3. This 4 is not 3, we would change it 3 with a cost of 3. This we can keep it because it is already 3. This 2 we can change it to 3 with a cost of 3. 2 can be changed to 3 with a cost of 3. The total cost here would be 4 times 3, which is 12. So 12 is definitely greater than 4. So 4 was a better option for us if we are looking to minimize the cost. So what we can actually do, we can just iterate through all the possible values of x and check our answer. So if we are, so how many possible values of x can we have? Let's look at a constraint first. We have n up to 2e5 and we are given ai is up to n only. Okay, so ai is up to n, so all the elements of the array are in the range from 1 to x. So at max, we need to iterate our x from 1 to n, not greater than n. Okay, if all the elements are less than n, why to waste a cost of greater than n times? That would definitely be more. Okay, so we would iterate our x from 1 to n. That's the all possible x we can have. And from 1 to n, for each x, if we can calculate the cost in O of 1, then our algorithm would be O of n, that would be accepted. So how can we, for a given x, if we are given an x, let's say x is 4, how can we calculate the cost in O of 1? For that, what we can do? What is the cost? If here x was 2, what was the cost? It was 2 times 2, which is number of elements which are not 2 times 2. That is for this x equal to 3, what we had? 4 times 3. What was 4? Number of elements which were not 3. So what we can do, we can say for any x, our total cost is number of elements not x, which are not equal to x, multiplied by x. That's our total cost. Now, how can we calculate number of elements not equal to x? That's total number of elements minus number of elements equal to x. what is number of elements equal to x? We can say it as frequency of x. Okay. If we can calculate the frequency of any element, we can say there are this many, the frequency of x many elements which are equal to it. So if you subtract that from n, we will get the number of elements not equal to x. This multiplied by x would be our total cost. So our cost is this for a given x. So what we can do, we can compute a frequency array first. That would be a pre-computation path. So from the given array, we would compute a frequency array which would store the frequency of every element. So how we can do that? We can just take a frequency array of size n. Okay, we can initialize each frequency with 0. Okay. And then what we can do, we can just iterate through for like each I in the given array. For every element in the given array, we can do frequency of I plus plus. This way we can compute our frequency array. If you do like this, we would, so frequency of any x would give us the how many times x occurs in the array. Then what we can do, we can iterate for each I from 1 to n. That's what we need to do. So we'll iterate for each I from 1 to n. And what we would do, we would say our cost is, as I had written above. What's our cost? It's n minus frequency of x multiplied by x. So cost can be written as n minus frequency. We have already pre-computed our frequency multiplied by x. And this cost we can just minimize. So we'll just take our variable answer, initialize it with some very big value, some infinite. Okay, sorry, we have to minimize. So we'll initialize it with some big value, and we'll say answer equal to min of answer comma cost. This way we can just minimize, get the minimum cost in our answer, and then we can just see out answer. So this way we can just solve this problem. Okay, I hope it is clear. I've also written the code, so we'll look at the actual code now. Okay. Minimum three. Okay, some people had written some solutions, so I hope this logic is clear to all. Some people have also explained why your solution is wrong, so I hope it's clear now. Or if I think any doubt is there, you can write down. Okay, so now we can look at the code. So what I did, I just this is my array, so I just took the input C in AI. So I took the input. Along with that, I pre-computed my frequency array. So the frequency array, I took a size of n plus 1, so it would have indexes from 0 to n, and I initialize all to 0. So initially, I have a frequency of 0 for each element. Whenever we get an element AI, we'll update the frequency of AI plus plus. So our frequency array is created like this. We have made our frequency array. Now we'll initialize answer with infinity. So infinity is actually a big number. If you see, infinity is in 64 max in my case, which is the approx the 4E18 or something. The greatest long value is okay. You can just take it like 1E9 also. It would be okay. So just take a big value so that when you minimize it the first time, you get the first value. Okay, so now I'll take my cost as n minus frequency of I into I. This would be my cost. I wrote the formula for cost, and then I minimize answer with min of answer comma cost. So let's see how the answer goes. I got it. Okay, so I hope this problem is clear to you. Max number of operations always, and yes, obviously, because number of operations would be n minus some frequency, so it would be obviously max it always. Like if you have any doubt, Garv, or is it clear? Like, you had written make all one, so uh, clear. Okay, so I hope that is clear. You cannot make all one. Maybe you had all twos and one value which is not two. So picking a two would be better because in less number of values we are applying that operation. Okay, so you would have to check for each uh, x. So now let's move to the second problem, so which is amphibian escape. Seth is building a robot frog, which he would like to be able to climb out of well quickly. The well has a height of h units. Initially, the frog is placed at the bottom of the well. Uh, A denote the jumping power of the frog, and B denote the slipperiness of the well's wall. The frog is initially at x equal to 0. Every second, the following two steps happen. So basically, we are given a well. The well is of a height of h units, and initially the frog is at the bottommost point of the well, which is denoted by x equal to 0. The topmost point would be x equal to h. Okay. So initially the frog is at this point. Now, what happens? Every second, two steps happen. So in every second, two things would happen. First, the frog will jump a units upward along the well. So first, what the frog will do, there are two values also given, a and b. So he can jump a units upward. So x will increase by a. If it reaches a height of h units or greater, with this jump, it's considered to have climbed out of the well and the process stops. So with this jump, if he goes above the level of h, so if he comes out of the well, the process stops. If he doesn't come out of the well, so if he makes a jump of a units and still he is inside the well, then slip b units downwards, that is x will reduce by b. So he would slip b units downward after that. So note that x cannot fall below 0. So x would just fall by b, and if this is getting negative, it would be taken as 0. It won't fall below 0. Okay, so now what we are given? So this is the thing with that would happen every second. So in 1 second, a jump and a fall, two things would happen together. And if the jump takes him out of the well, then the fall would not happen. He's out of the well. So Seth hasn't decided on the jumping power of the robot frog and doesn't know the slipperiness of the well. You are given integers k, n, k, and h. Count the number of pairs AB such that A is in the range of 1 to n, B in the range of n, 1 to n. If frog had jumping power A and well slipperiness is B, the frog can escape well, which has height h within k seconds. So basically, as an input, we are given three things, n, k, and h. What we need to find, that we need to find the number of pairs AB. So we'll just assign A and B different values. So we need to find how many pair of different values can we have, such that A lies in the range from 1 to n. So we can assign A values from 1 up to n, 1, 2, 3, 4 up to n. For B, we can assign values 1, 2, 3, 4 up to n. And if and now with this particular values of A and B, you have to determine whether the frog can escape the well. The height of the well is h within k seconds. So it would take some time for the frog to escape. You have to find whether he can escape within k seconds. So how many pairs of A and B exist so that he can escape within k seconds? That's my question. We have to count the number of pairs of A and B. So and our constraint is n is in the range of 2e5. So A would have from 0 to n, B would be 0 to n. So if you like just brute force it and look at every pair of A and B that exists, it would be n into n. There would be n values of A and n values of B. So n square pairs would exist. So you can look here that you cannot go O of n square. So you cannot just check, go to every pair and then check. Okay. So you'll have to optimize it a little. And k is 1e9. Okay. The number of seconds can be up to 1e9, height can be up to 1e9. Okay. So now let's see what we can do here. Okay. So what we are given is, we are given three integers. We are given n, k, and h. Three integers we are given. So h is basically the height of the wells. Okay. So we would have some well which is having a height of h. So this is h, this is 0. Okay. So we'll have 1, 2, likewise up till the highest point is h. So this is our well. And then we are given n and k. So k is just the maximum time. Okay. So this is the maximum time we have. So within k seconds, the frog has to come out. And n just denotes the range of a and b. So we have to find different values of a. So a would be in the range from 1 to n, okay, and b would be in the range from 1 to n. So we have to determine different ranges of like different values of the pair a comma b. Okay, so what we can do, let's say n is 5. It means we can, what pairs can we pick? Okay, let's say n is 2 only. Okay, let's say n is 2. What all pairs can we have? We can have a equal to 1, b equal to 1. That is one possibility. We can have a equal to 1, b equal to 2, a equal to 2, b equal to 3. So these are the pairs of a and b that we have. So we have to find Okay, is my voice audible? Sorry, I got disconnected. Sorry, I got disconnected. Okay, I'm sharing my screen. Okay, like, can you still where I got disconnected? Like, I was explaining this part that if you have n equal to 2, then you can have these pairs. Okay, so like, was this part like till where I got disconnected? Can you just tell? Do I need to repeat this part? That okay, I was explaining this that you can have, you are just given in input n, k, and h. So h represents the height of the well. Okay, so the well can be uh, these are the coordinates of the well starting from 0, 1, 2 up till h. H is the maximum height, and then k represents the maximum time that we have, and n is the range for a and b. So we have to pick a's, a in the range from 1 to n and b in the range from 1 to n. So among all the pairs of a and b that we have to find how many pairs are there so that the frog can reach out of the well within k seconds. Okay, that's what we need to find. Uh, okay, so now what I was telling is, let's say you had n equal to 2. So if you had n equal to 2, that means what all pairs of A and B can you have? You can have A equal to 1, B equal to 1. You can have A1, B2. So like this, A2, B1, A2, B2. So for n equal to 2, you can have these four pairs of A and B. Okay. And for these pairs of A and B, you have to find these pairs come out of the within k seconds. So let's say k is, for this case, okay, let's say we have taken k equal to 5, and let's say h is taken as 3. Okay, okay, or let's say k10, h is, okay, h is taken 8. Okay, let's say this is the test case, n is 2, K is 10, H is 8. So we would, so first the brute force approach would be check for each pair. Okay, let's say we are checking for each pair. So for A equal to 1, B equal to 1, what would happen? The frog is at 0. He would jump A units up, and then he would fall both A and B are 1. Next second, he would jump to 1, fall to 0. Again, jump to 1, fall to 0. So this would occur till infinity. So that is, you just cannot come out of the well in this case. Okay. So in this case, this would be a no. Now A equal to 1, B equal to 2. What would happen here? So here A is 1, so you can jump 1 unit. B is 2, you would fall 2 units, but you cannot fall below 0, so you would fall to 0. Again, 1 unit jump, fall 2 unit, so you would just fall to 0. So again, you till infinity, you would remain at 0. So not possible for this case also. Now A equal to 2, B equal to 1, what would happen? You would jump 2 units up and then fall 1 unit. Okay, so you would be at 1. Then again jump 2 units, fall 1 unit. So you would be at 2 after 2 seconds. After the third second, plus 2 minus 1. So you would be at 3 after 3 seconds. Plus 2 minus 1. You would be at 4 after 4 seconds. So likewise, you would go. When would you come? After how many seconds would you come out of the loop? Out of the is 8 here. So if we draw 3, 4, 5, 6, 7, 8. So what would happen? At t equal to 1, at t equal to 0, you are at 0. At t equal to 1, you jumped 2 and fall by 1. So you came at 1. Then a jump of 2, fall of 1. At t equal to 2, you came at 2. So likewise, if you saw jump of 2, fall of 2, at t equal to 3, you came at 3. So after like this, you would go, and at t equal to 7, you would be at 7. Okay, so from 5, you jumped, from 6, you jumped 2, and then fall 1, you reach 7 at t equal to 7. Then at t, okay, not 7, at 6, you are at 6. Okay, so at t equal to 6, you were at 6, jumping from 5 to 7 and then a fall. Okay, like that you came to 6 at t equal to 6. Then after that, from 6, you will jump to and reach 8. Once you reach this height age, you are out of the loop, out of the well. Okay, so at t equal to 7th second, you would come out of the well. So if you would take 7 seconds to come out. So you had 10 seconds, so 7 is enough. It would be right. Okay, so you see, you were jumping by 1 unit if you see effectively. So A minus B was 1. So you were doing plus A and then minus B at each step. So a net of A minus B, you were jumping each seconds. So a net of 1 each second. So if you had a height of 8, it means after 8 seconds you would reach the come out of the well. No, here you came out in 7 seconds only. Why? Because till 6 seconds you were at 6. Okay, till 6 seconds you were at 6, but in the 7th second you jumped to 8, and then you just came out of the well and did not fall. So actually, one time you can just jump and not fall if you reach out. So so like we'll look what formula we can derive. So like this was the basic thing. So in this case, if you take A2 and B2, then jump of 2, fall of 2, jump of 2, fall of 2, you cannot reach. So here your answer would be 1. There is only one we can get an answer. So the answer would be 2. Now let's look for a generalized way what we can do. So what you can see, if you have a well of height h, so then what you are doing is from 0, you would jump to A and then fall to A minus B. Okay, this point would be A minus B. So, and then again plus A minus B. So each step you would do an increment of a minus b. If an increment of a would not take you out of the well, then you would do a minus b. If it takes out of the well, you would just do a plus a. So when would it take out of the well? When you are at some point, let's say x, such that x plus a is greater than equal to h. So when you reach a point x such that x plus a is greater than equal to a, then you would come out in one step only. But before reaching this point x, the number of steps or number of seconds would be whatever this height is. So whatever this height is, so this height was h minus x. Okay, this is the height divided by, in each step you are doing a minus b. So you can write like this, that because till here at every step we were doing plus a minus b, plus a minus b. So effectively you can say you were doing a minus b in each step. So how many steps would take you to x? Okay, sorry, this is not h minus x, this is x only. This height is x actually. This was h. Okay, from this is 0, so we are counting from down. So you would take x by a minus b. This would be the number of seconds it would take to reach x. After x, you would jump and reach out of the well. So what would that x be? That x is basically, when can you jump out of the well? This is greater than equal to h. It just implies x is greater than equal to h minus a. So whenever you reach a point greater than h minus a, so this is actually, so if you have a well, this point is h, you can write this point h minus a. So from this, whenever you jumping, you reached a point greater than this, greater than equal to h minus a point. After that, you can just do it in a single jump. So the if you look at this h minus a, so you are actually number minus a. So that you can calculate. So it's h minus a divided by a minus b. So this would be the number of seconds to reach above this seal value of that. Because if this is, let's say, 3.5, then you would complete that jump. So you would take the seal. Okay, so you would not, if you take the floor, you would reach just below h minus. If you take the seal, you would reach just above h minus a. So the seal of this, okay, and plus one more second to jump out of this, out of the well. So basically you can say this is our formula. If we are given a and b, then this much time it would take to jump out of the well, and if this thing is less than equal to k, then we can just say yes, this pair of a and b can exist. We would add plus one. But if we do like this, if we go to each pair of a and b, it would take o of n square, which won't be accepted. So how can we optimize it? Now to optimize it, what we can see, instead of iterating through for all a from 0 from 1 to n, and then for all b from 1 to n, instead of doing that, let's say we iterate only for all a's. Okay, if we iterate only for all a's, let's say we fix an a, we iterate for, let's say we are at a equal to 2, we take a equal to 2, then we just need to count how many values of b can we have, so that it comes out in k seconds. So we can see, if let's say for a equal to 2 and b equal to 1 satisfies our condition. Okay, let's say a is 3. If let's say a equal to 3 and b equal to 2 satisfies our condition, if let's suppose this satisfies, then would a equal to 2 and b equal to 1 satisfy? What we can say, just by looking at this, it would. Yes, it would. Why? Because if we are reducing only the value of b, we are reducing the slipperiness. If we are reducing the slipperiness, definitely, if it was able to come with a slipperiness of 2, out with a lesser slipperiness also. Okay, so what we can say, for a given a, if we can find the maximum valid b, if we can find the maximum valid b, we can say all the b's from 1 to, if this maximum valid b is mx, we can say all the b's from 1 to x would be valid. So we can just add a plus mx to our answer. So we would have mx number of pairs of a and b that would be valid. So for a given a, we just need to find maximum valid b. Okay, then we can just add plus mx to our answer, and this way we would just need to iterate to all the a, and we can compute in O of n. Now, how can we find the maximum valid b in O of 1? Okay, so that's now our question. How can we find the maximum valid b? So you can just look at this formula. So let's write it again. It was h minus a by a minus b. So what was the condition for a and b to be valid? Minus a minus b. This, the ceil of this plus 1, it should be less than equal to k. Or we can just, I'm just changing it a little bit. What we can say, we can take this here, plus 1 that side. So we are just saying in k minus 1 seconds, if we can reach a height of h minus a, then it is valid. So what is the maximum b that satisfies it? So we can just either just change this relation into relation of this. So we can take that there, and it would be h minus a by k minus 1. So b would just become a minus h minus a by k minus 1. You can do the mathematics thing. That way you can compute the maximum b. So, or you can just look at it and directly compute. So what the maximum b you can get, it would actually be, okay, so one way is just derive formula like this. It would be c here. Okay, or another way I'm telling is, this point is h minus a where we want to reach. So we can calculate what is the maximum required to reach it within k minus 1 seconds. So h minus a divided by k minus 1, this ceil, this value is going to give me in each second how much we need to travel so that we can reach in k minus 1 seconds. So we need to travel in each second at least this much. And what is this? So this is our requirement to travel in each second, and this requirement is actually b minus a. That's the thing we are traveling in each second, the net. So we can just say that our b minus a should be greater than equal to h minus a by k minus 1 c like that. Okay, so like you can do mathematics and whatever, you can just derive this. Okay, it was not so complex to derive this, just you had to find this h minus a divided by k minus 1 would give the steps required in each second. So h minus a by k minus 1, the ceil of that. And so that should be b minus a. So b should be greater than equal to, okay, sorry, that's a minus b. Okay, that was a minus b is our next step. So b should be less than equal to just a minus this thing, h minus a by k minus 1. Okay, so this is the maximum value of b. So this you can say this is mx. So you can just add plus mx to your answer. All the b's from 1 to mx would be valid. Okay, so you can just compute this mx and add plus mx by iterating through all the a for all a from 1 to n. You can just iterate for all a from 1 to n. You can calculate this mx and add plus mx to your answer. This way you can compute. Okay, I hope it is clear. Okay. Yeah. Okay, so now we can look at the code. So basically, as I told, we took the input n, k, and h. We iterated for all a from 1 to n. Okay, so this basically is a loop from 1 to less than equal to n. Okay, it is less than n plus 1, not till n plus 1. Okay, so we are iterating from 1 to less than equal to n. And then if the first thing is, if in one step only you are able to come out, if a is only greater than h, it means you can just take any b, it does not matter. You would always come out in one step, and k is always greater than equal to 1. So it would always be valid if A is greater than H. Okay. So that's a small base case that if A is greater than H, it means in one step you would come out. So you can just add plus N to your answer, means you can have any B from 1 to N. Okay, so all valid combinations of B's from 1 to N is valid. So add plus N to our answer and continue. Okay. So the requirement is H minus A by K minus 1. So you are taking the seal of that. So how you take the seal? This division would give you the floor. And if this division had a remainder, you can add a plus plus. So this you would get a seal. So basically, this is one way to compute seal, that you take the floor by dividing it, doing an integer division. And then if this modulo this is greater than zero, writing greater than zero or not would not affect if condition. So if this is greater than zero, it means we get some remainder, then a plus plus to our answer. So this would give us the seal of H minus A by K minus 1. So mx is A minus the seal of H minus K1. So it was A minus the seal of this thing. Okay, so A minus required is our mx. And then if mx is greater than 0, okay, like it may happen, then we may get a negative value of B. So in that case, we would just add plus mx to our answer. So negative value of B, it means whatever B you choose, you cannot come out of the well. Okay, you cannot have negative value. So then you would just add plus 0 to your answer or nothing. So if you are getting a positive value of B, then only you would add plus mx to your answer. Okay, otherwise not. So this is our code and we can just pick the answer. What would the complexity of the code be? We are iterating from 1 to n. So O of if O of 1, this calculation of 1, this is O of 1, again O of 1, O of 1. So all these are constant time operations. So constant time operations inside a loop of n. So we can say it is O of n. Okay, that's our time complexity. Okay, I hope the second problem is clear. So can we do binaries? Yeah, you can do like uh, through the formula we were computing. Another way was, if we had computed the formula for this, we could have done a binary search. Like we had computed this formula, you need to find the maximum B so that this thing is satisfied. So you can do a binary search and find that maximum B. So that is also okay. You can do it in n log n. Okay, so if you have derived this formula, then no need to derive that formula. You can do a binary search. Okay, so that's another approach. Okay, so now let's move to the C problem. I hope this is clear. Nobody has any doubts in this. Okay, so what we are given in the C problem, a permutation of length n is an array of length n that contains every integer from 1 to n exactly once. For example, this is, so we are just given the definition of a permutation. So if you don't know what a permutation is, it means an array of length n such that every integer from 1 to n occurs. So if n is 3, it means 1, 2, 3 would occur. So uh, in some random positions, but one all each from 1 to 3 would occur. So these are some permutations of size C, and this is not. So that's the definition of permutation. Beauty of a permutation P is defined as the number of prefixes of P that are themselves permutations. That is, it is number of integers I such that this array is a permutation of length I. Okay, so what we are given, we are defined a beauty of permutation. What does the beauty says? It is the number of integers I. So number of such I is an index, either from 1 to n. So number of such indexes I such that this permutation from 1 to I. So the if you take the subarray for that permutation from start till I, then that subarray should also be a permutation of length I. If it satisfies this thing, then we would add a +1 to our answer, and that just means the number of i's that satisfy this thing is our beauty of the permutation. That's the definition of beauty. You are given a permutation P of length n, you can perform following operations on it at most once. Choose two integers L and R such that L and R are in the range of and L and R have different parities. That is, L is odd, R should be even, and vice versa. Then for each I from these, swap Pi and Pi plus 1. Okay. So basically, what we are given a permutation P, and then we are given some type of operations. What we can do in a single operation, choose an L and R. So we are choosing a range actually of L and R, and they have different parities. That simply means you have to choose a range, a even range. Okay, so if your L, the starting L is 2, and you pick a R which is 4, that is not valid. You have to pick an odd R. So odd minus even plus 1 would give you even. Basically, you are, in simpler words, same thing is written, that you have to choose a subarray of even length. That's what the it means. They have different parity. It means the same thing. You have to choose a subarray of even length. And partition, and then after choosing a subarray of even length, what you do, you go to L, L plus 2, L plus 4. So every alternate index you would go and swap Pi with Pi plus 1. So you would swap the first two values, next two values, next two values. That way you have to do. Okay, that's what it basically means. So if you have this permutation, you choose L equal to 2, R equal to 5. This is L equal to 2 to R equal to 3, 4, 5. So this is the range that we choose from 2 to 5. So we swap the first two elements, made 5, 1. Swap next two elements, made 6, 2. So that's what we converted it to. Okay, so I hope the operation is clear. Now find the maximum possible beauty of P after performing at most one such operation. So you have to find what is the maximum possible beauty of P after performing this operation at most one time. So you can perform this operation only one time, and after performing this operation one time, you need to find maximum possible beauty of P. So beauty was defined here. Okay, so this is the problem. Let's see what we can do here. Okay, so if you have this permutation, so like I'm again taking zero based indexing here. Okay, let's take one based only. That would be easy from this one. Okay, let's say this is our permutation. What does that mean? It's a permutation, so obviously for the first all five elements, there would be all five elements one time. That's what a permutation is. So from one, two, three, four, five, all would exist here. Now, what is beauty? Beauty means if you would go for each I. So first, let's say you pick I equal to 1. You would check whether this is a permutation. So you check 3. 3 is not a permutation of length 1. So if you're going to I, you would check permutation for length I. So a permutation of length 1 would include just 1. You cannot have greater than 1. So this is not. Now you picked I equal to 2. You checked whether this is a permutation. So for I equal to 2, you can have 1 and 2. You cannot have 3. Again, this is not a permutation. Now you chose I equal to 3. Okay. So you checked whether this is a permutation. So for I equal to 3, you should have 1, 2, 3, but you have a 4 here. So this is not a permutation. Now you checked for I equal to 4, whether this is a permutation. So for I equal to 4, for a permutation, you should have 1, 2, 3, 4. You have 1, 2, 3, 4. So this is a permutation. Okay. So for I equal to 4 is a valid case. Before that, all were invalid cases. Now for I equal to 5, for I equal to n, you would obviously get a permutation because for this full subarray is you are given that this is a permutation. So I equal to 5 would obviously satisfy this condition. So the beauty of this given array is 2 because there are two values of I that satisfy that 0 to I is a permutation. Okay, so currently the beauty is 2. Now what you need to do, you need to perform some operations and change its beauty so that you can maximize the beauty. You want to increase the beauty. Okay, so for that you need to perform the operations. So, okay, now what operations can we perform? Let's see. Uh, so you can select a subarray of even length. So let's say you selected this subarray of length 4. So if you selected this subarray of length 4, what does it mean? You would form pairs of two elements in that subarray. Because you have an even length, you can form pairs of two elements. So for every pair, you would swap that pair. Okay. So you formed this pair, you swapped these two, you swapped these two. So it became 3, 4, 1, 5, 2. That's what it became after swapping. Okay. So now if we again check, then we can just again check what's the beauty of the array. Okay, for this, for this, for this, for this. But now let's try to think which operation would we perform so that we are increasing the beauty, the maximum. So for that, you would have to think what change are we making by performing an operation to the beauty of that. That's what matters. Whenever you want to maximize something by performing some operation, always think like this. What change are we making to what we want to achieve? So we want to maximize the beauty. What change are we making to our beauty by performing an operation? So let's try to think here. What change are we making? Okay. So uh, what's my operation? My operation is from an array, just select a range, and then let's say you selected this range. Then for this full range, divide it into pairs of 2, just swap all the pairs. So basically, your operation is if you are swapping, let's say, some two pairs, it means if you take this swapping of a pair as an operation, it means you can do this for some consecutive pairs. Okay, so if you swap these two, you can swap these two, these two, you can swap these two, these two. So the pairs you swap all should be consecutive pairs. So then you can say that you are performing an operation for this range. It means you are swapping all this. Okay. So basically the operation is swapping of two indices. Okay. So let's say, let's try to think what change we are making to the beauty of the array by swapping two numbers. So if we swap two numbers, let's say we swap these two numbers. Okay. Okay, let's clear it a little bit. Let that be. So initially what we had, that we had that this, these three at these three indexes, uh, it was not satisfying the condition for beauty, and these two indexes were satisfying the condition for beauty. Okay. Now, if we swap these two, what change would happen? Okay. So let's see if we swap these two. So first thing is, if you check for this pair, okay. So let's recheck all pairs after swapping these two. So for this pair, for this to be a permutation, only this element matters. So if we are swapping these two, this would never get affected. So whenever you are swapping two numbers, all the elements before this, for these, this, it was a cross or a tick, that won't get affected. That's the first thing. So if you are swapping these two, if you had like more elements here, all those would never get affected because they does not depend on these. Now, what would happen to this for I equal to 2? I equal to 2 is this thing. Now, before I equal to 2 was 3, 1. Now, after swapping, it would become 3, 4. So, still 3, 4 is not a permutation. But this could have made a change to our answer, we can think. When? So, basically, it's whatever, if we are swapping these two numbers, whatever permutation we had here, if you remove this and add this here, and now if this thing becomes a permutation, then we can say it was not a permutation earlier, now it became a permutation. If that happens, that by replacing this becomes a permutation, then we can, so we can just represent that change as a +1. Okay, so we can check that if we are swapping these two numbers and this is changing from not to a tick, then we would store a plus one at this index. Yeah, that this index can be made a plus one by performing an operation for this pair. Okay, so that's a thing that we can do. Now let's check if we are performing an operation in this, what would happen to for I equal to 3. Okay, for the check of I equal to 3, is it is I equal to 3 a valid permutation from this means, is this a valid permutation? So if you look at this, if we swap these two, would the elements in this subarray change? The only the order of this would change, but whatever elements were there, it would remain the same. So swapping these two is not affecting this subarray. So that means if we are swapping these two, it would only affect this. Now, if you look at somewhere here, I equal to 4, is it affecting this? These two are just swapped. Why would it affect this? Only the positions are changed. But for a permutations, the order does not matter. If you are checking just whether it is a permutation, all the values from 1 to 4 should be there. It is still there. If you have 4 here, 1 here, no problem. All values from 1 to 4 are still here. Okay. So that means, what does that mean? That whenever we have an array, okay, and some indexes, if this index is I, okay, so if we are swapping I and I plus 1, it can only change our answer for I, not for any other index. Okay, so our answer for I just mean whether for I the beauty condition is satisfied or not. When the beauty condition was how many I's exist for which this condition, this subarray is and this that. So I if we are swapping these two numbers, it can only change our condition for I, not for any other index. So we can just store for each I. Okay. Now initially we stored for each I that cross 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 tick tick. What does it show? We can also like store it in 0 1 0 0 1 1 1. It shows that for I equal to 1, the condition was not valid. I equal to 2, not valid. 3, not valid. For I equal to 4, it was valid. For I equal to 5, it was valid. So if you store it like a 0 1 and then take a sum of this would give our beauty. Okay, the sum would give me the beauty. Okay, so this is one way of storing. Now we are just calculating the change in this array. So if for any particular index I, if swapping these two numbers changes from a state of 0 to a state of 1, so we can store in another array the change. So it means if applying an operation on I, you can just understand that from this example. We were performing on these two. What if we perform a swap in these two numbers? Okay, let's see if we swap these two numbers. We made it 4, we made it 2. Okay, we perform the swap. So if we are performing a swap in these two numbers, okay, with I and I plus 1, this is my I, so I would check for this, only for this, no other would change. Now let's check for this. It's I equal to 3, we need to have 3, we have 1 2 3. So it became a valid permutation, which it was not before. So we actually changed the state from 0 to 1 by performing an operation on I equal to 3. Okay, swapping 3 and 4. So at 3, I can just store a plus 1, representing that we are change. If we perform an operation at this place, we are changing from 0 to 1. So we are doing a plus 1. And let's take another example that I swapped these two indexes. Okay, so whatever I had before, okay, so I had 4 and 2, whatever I had, let's say I swapped these two indexes, that would become, so it would become 2 here and 5 here. Okay, so before at I equal to 4, this was a valid permutation 1 2 3 4, but now if you say it has a 5, which should not be here. So we changed the state from 1 to 0. It was a valid permutation before, now it is not a valid permutation. So for this index, we would store a -1. That if we perform an operation at this index, we would we are decreasing our beauty by 1. Okay, we are doing a -1 to our beauty. Okay, so this is the first thing, that for each index we can like this. If no change is happening, we would store a 0. Okay, so like for each index, we can just compute this thing, that if we are swapping, like for each I, we would compute, if we swap I and I plus 1, what change we make to our beauty. That's what I would store for each I. So let's say I'm naming this vec. Okay, so vec of I represent this thing, that if we swap I and I plus 1, what change are we making to the beauty of our chain array? So let's say so you can find this. Okay, how you would compute this, that we would discuss how you can find this veci. Okay, let's suppose I have created this veci. Okay, so I'm trying to explain my intuition, what things I tried in the contest during, so how I came up to the solution. So I just tried to think if we can compute the change. That's what I told, if we can compute the change. So now I computed this change in a vector. Now how I would compute that, I would think afterwards. Let's see if we have computed this change, can we calculate our answer? If let's suppose somehow I calculated this change. Now if I calculated this change in a vector and I stored this, okay, let's say this is a change, +1, -1, 0, 0. These are the changes. Now what's my answer? I have to perform, what's my operation? I have to take a range from L to R and that perform operations. Uh, it's just swap two consecutive. Okay, so that means if I'm performing an operation from, okay, if I'm performing an operation in this range, it means I'm swapping this and swapping this. So it means I'm applying operation, I'm changing this thing and this thing. Okay, if I'm applying operation in this for this range, I'm swapping this and swapping this, means I'm changing this and this only, not this. To change this, I would need to swap this. Okay, so if you look at this, if I'm applying operation here, I'm swapping these two indexes. So if I'm swapping I and I plus 1, I would affect this change, what I have stored here. I would affect that change. And if I'm swapping these two, I would affect this particular change. So that is means I am affecting alternate changes. So whatever array I got, so either I would change the odd indexes of this, I would affect these changes, or I would affect these changes, and for a particular range. So basically now my question reduces to uh, find that range. So if there can be two cases, you are taking L as odd, it means you are doing for odd indexes. If you are taking L as even, you are doing for even indexes. So this particular array that you got, you can break it into odd indexed array, even indexed array. Then you just need to find from this odd indexed array. So either you can pick, if you are just taking odd, so you can, if you pick L as this, R as this, you are doing inflicting all these three changes. If you pick L as this, R as this, you are inflicting these two changes. If you pick L as this, R as this, you are inflicting only this. L as this, R as this, only this. L is this, R is this, only this. So you can understand, basically among the odd indexes, if you make an array of the odd indexes 0, 1, 0, you just need to, you can do any subarray of this. It means you just find the subarray with maximum sum. Okay, the question reduces to finding the subarray with maximum sum. If you can find that, that's your, that's the answer you are adding to your actual answer. Okay, That's the beauty you are adding to whatever you had earlier. So you can calculate the beauty of your original array and then add plus this thing, subarray with maximum sum for odd indexes, same for even indexes, 0, 1, 2. For this also you would calculate. So the maximum of among these two, you would add that to your answer. Okay, like, did you got this logic? Yes, Kadani's algorithm. You would use Kadani's algorithm basically to find the subarray with maximum sum. Okay, so I hope this part is clear that if you can compute this vector, what was this vector? This was representing my change if I swap I and I plus 1. That's what each index was representing. So these changes I can inflict alternatively. So I would take the odd indexes and even indexes. I would apply the Kadani's algorithm to find subarray with maximum sum for this, and the same I would apply to form this, and the maximum among these would be added to our original beauty of our original array to get the maximum beauty we can obtain after performing the operation. Okay, so if this part is clear, then our only challenge is how can we compute this vector? How can we compute this vector when we need to find the change we are making if we swap I and I plus 1? We need to compute that thing in O of n or n log n. Okay, not n square. Brute force approach would be just go to each I, compute that change, look for this vector just included and I plus 1 included. But here n square would not work. Okay, n is 5e, 1e5. Okay, so n square would not work. So how can we compute this in n log n? So we can see, okay, let's take this. Okay, let's take a better example. Let's say 3. Okay, let's say something like that. Okay, let's take this array of size 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. This is, we are given a permutation of size 8. We need to compute for each index. For this index, if we swap these two, whether this, okay, first let's compute for each index whether it is a permutation or not. Okay, so first let's, so that we can calculate the beauty of our original array, we also need to calculate the beauty of our original array. So let's just, this vector would represent that is it is this valid I or not. Okay, so what we can do, first I would check for I equal to 1. So 1, 2, 3, 4, I'm doing the indexes. First I would check for I equal to 1. For I equal to 1, I should have only 1. We are having 3. Okay, so this is not valid. Now for we would check I equal to 2, we should have 1 and 2, but we have 3. So this is not valid. I equal to 3. Okay, so now you can just feel how can we do this thing. Okay, if you are checking for all, that's brute force. So so what we can do, when we are at this and then we move to this position, in a set we can store the values that we have got till now. Okay, so if we store in a set, if we store 1 and 3 in a set and then take the maximum value of that set, if that maximum value is greater than I, it means it's invalid. If it is equal to I, it means it is valid. Okay, what I said, we can, when we reached 1, we can store in a set. Okay, it would be an empty set initially. Now when we reached 1, we inserted 3 into our set. Now we checked till 1, what should we have? We should have only 1. So if we look at the set, if we had all elements from 1 to 1, that is just 1, our maximum value would have been 1. So it should have been 1 for it to be a permutation, but it is 3. So it is not. Now what we did, we inserted 1 to our permutation. Okay, so to our set. Okay,
to our set we inserted a 1 when we reached 1. So then we checked. For this subarray R is 2, we should have 1 and 2. So maximum value in the set should be 2, but we have a 3. So I would say it is also invalid. Okay. Then I inserted 4. I inserted 4 into my set. Then I checked. For I equal to 3, I am checking. So it should have maximum value of 3, but we have maximum value of 4. So I can say this state is also invalid. Then I checked for, I inserted this 2 here. Okay, I made this set as this. Okay. Now I check the maximum value in the set is 4 and I is also 4. Okay, so if the maximum value is valid, that is for this subarray, I'm storing all the values in a set and the maximum value in the set is equal to I. It means we have all elements from 1 to I. A set stores only unique elements. And if the maximum value is 4, it means we have all elements from 1 to 4 in this set. So it is a permutation of 4. We can say it is valid. Now, same way, we can just go to 7 and just insert here and maximum value is 7, so not valid. Inserted a 5 here, maximum value should be 6, but it is 7, so not. Inserted a 6 here, maximum value should be 7, it is 7, so it is a valid permutation. Inserted a 8 into it, so maximum value set should be 8, it is 8, it's a valid. So this way we can just compute which are valid and which are not valid. So we have 3 ticks here, so we can just say, just do a plus plus and we can compute the beauty of our original array as 3. In this way, in O of n log n, we can compute the beauty. Now, along with beauty, I needed to compute this vec. Okay, this thing also I needed to compute. How can you do that? So just twist this algorithm only a little. Okay, so when we reached, let's say this index, we inserted 4 into our set and then we checked it was not valid. What if had we swapped these two? Okay, so what Vekai stores that had we swapped these two, what change are we making? So first compute, insert 4 and then compute, is it valid or not? Okay, let's say it is not valid. Then remove this 4 and insert 2. So you can just erase AI and insert AI plus 1 into your set. Then again check. If now after this insertion, so what we had here, okay, in our set, we had 1 and 3. When we reached 4, we inserted a 4. So now what we did, we checked. Maximum value is 4, I is 3, not valid. Okay. Then what we did, we removed this 4 and inserted this 2. So we removed this 4 and inserted 2. We removed AI, inserted AI plus 1. Now check the maximum value in the set. For this set, maximum value is 3. I. So now it became valid. Changed from invalid to valid. So in our vec, we would store a plus 1 here. Okay, so whatever we had there, we would store a plus 1 at this position that if we apply this operation, we are changing from 0 to 1. Okay, and after that, we would again remove 2 and store 4 so that when we go to the next iteration, we only have these into our set. So again, we would erase 2 and store 4. Okay, so we are back to what we should have actually have in our set. So this way, along with computing this original beauty, you can also compute this vec by computing the change. Okay, I hope the logic is clear, algorithm is clear. Okay, so once you have computed this vec which stores the change, after that the step is for all alternate indexes, compute the maximum subarray sum, and among these two maximum plus the actual value of that you computed, actual beauty of the array, that would be your final answer. I hope the logic is clear. We can move to the code now if there's any doubt. Yeah, we would discuss the decryption also. Okay, so we would move to the code now. Okay, so you can see first I took the input
Okay, that's the input part. Then I created this vec as I told in my explanation. What I told, that's what it. I've created this of size n minus one only because for the last index n, you don't have a n plus one in your array. So it means you can never do any change. You cannot apply an operation there. So there is no need to calculate for the last index. Okay. There is no n plus one nth index after that. So you cannot apply a swapping operation on the nth index. Okay. That's the first thing. And here I have taken zero based indexing. So my last index is n minus one. So instead of, okay, so now I've taken zero based indexing. I'm going from zero to n minus one. I would insert AI into my set. Okay, first thing I inserted AI into my set. Then I checked the maximum value is my set. What is maximum value? Set dot r begin is going to give me the maximum value iterated to that and star. So this is going to give me the maximum value in my set. If this is equal to I plus one, because I have taken a zero based indexing, it would start with I equal to zero. So I would check with I plus one. If you take a one based indexing, you would check with I. Okay, so this is my check. If this is satisfied, I would say this C++, it means the count of the actual beauty of my actual array. So beauty of my actual array, C is storing. Okay, so I did C++ and I did veci is equal to minus one. Okay, so why I did that? Because if at index I it is satisfying the condition, it means it is a one here. Okay, if let's say this four is was satisfying the this four was satisfying the condition, it means if you swap these two, if this was satisfying and instead of this you make enter anything else, surely it would unsatisfy after this. So for this, you can say your veci would always be minus one if this is satisfying. Then by swapping, you would always make it to unsatisfied because you're removing this two, taking it outside, but this two was required if it was satisfying. Okay, so I hope this logic was clear. That's why I directly did a minus one there and continue because I don't need to check swap and then check. It was satisfied, then after swapping, it would slowly become unsatisfied. Okay, so I did a minus one there. So it means if I apply an operation on this, my beauty would decrease and continue. Now, if this is not satisfying, then what we can do? We would check for the swapping case. If this is not satisfied, so whether can we satisfy it after swapping? So erase AI and insert AI plus one. Then again check. So I actually erased AI, inserted AI plus one, then checked. So if I had swapped, then this whether this satisfies. So if this satisfied, I would store vec equal to one. It means I'm changing from zero to one. I'm doing a plus one. Doing a change of plus one if I'm applying operation in this. So vec equal to one. If not, then I'm initializing my vec with zero. So it would be zero. That I'm making no change. Okay. So if you are not initializing with zero, you can do else vec equal to zero. Okay, so I'm initializing it here, so no need to write the else thing. And then since I had erased AI and inserted AI plus one, so I would again erase AI plus one and insert AI. Okay, to get back to our original state so that our iterations are not disturbed. Our set is containing elements before I only. Okay, so this way we have computed our vec. Then I would apply Cardani's algorithm of maximum subarray sum. Okay, so if you don't know about that algorithm, I'll just tell it's not, it's nothing. You initialize your maximum sum with zero and your initial sum with zero. Okay, then you move. Okay, we are doing for odd indexes and even indexes separately. So first we would do from like odd indexes starting from I equal to 0, 0, 2, 4. I would go for even indexes in a zero based indexing. Okay, I plus equal to 2 I'm doing. Okay, so I'm keeping indexes going to alternate indexes. So in this we just do sum plus equal to vec I. So we are just adding the current element to our sum
And then whatever sum we got, that can be our answer. So just maximize it. And then if this sum becomes negative, we'll do sum equal to 0. Okay, then we will reset that whatever sub array we had before, it was giving me negative value. So just ignore that. Make again, take an empty sub array, start from the beginning. Okay, so that's what, in this way you can find the maximum sub array sum. For even indexes, same thing for odd indexes. Again, initialize sum with 0. Same thing for I equal to 1, I plus equal to odd indexes. And then in mx, I got the maximum by doing max both at both places. I got the maximum. My final answer would be C plus mx. C was the beauty of original array. Mx is the extra beauty we can add using operations, maximum extra beauty. So that's our final answer. Okay. Yeah, this was a good problem. So I hope this is clear now. Okay, then we will move to the next problem, which is even. Okay, so I'll just take a breath. So then we'll move to the next problem. Okay, I hope there is no doubt in this problem. So we'll now move to the D problem of div 2. Okay, so in this problem, okay, like initial warning only. This is a little high level problem, so I won't go to like too much into intuition and everything in too much detail. Okay, I hope that you would be able to understand. I'll explain my logic. Okay, so let's see now. You have an array A of length n. You can perform following operations on it as many times. Okay. Uh, Choose two integers L and R. Delete the elements from AL to AR. So just delete all the values from the range L to R and insert the median of this range in their place. So basically just choose a range of L to R and delete that whole range and replace it with the median of that range. That's basically our operation. Here denotes the size and this and this. So for each I decide whether there exists a sequence of operations such that after performing the sequence, the resulting array is of length 1 and contains only single element AI. So what we need to find is, you are given an array, you need to find, you need to return a binary string. So what does that mean? You just need to return for each I. Okay, for I equal to 1, whether we can perform some operations to reduce this whole array into a single element equal to 1. If yes, then give a 1. Then check for I equal to 2. Whether can we perform some sequence of operations to reduce this whole array into a single element equal to 2. If yes, give a 1. Check for I equal to 3. Whether we can reduce this whole array into a single element through some sequence of operations, and that single element is equal to 3. If we can do this, do a 1. Otherwise, a 0. It means we can never do this. So that's what we have to output. I hope the problem statement is clear. For the median, it is given that if it has odd elements, then the middle, after sorting, the middle element is the median. If it has even indexes, then after sorting, the among the two middle elements, the left one is your median. Okay, so the left of the two middle elements is your median. Okay, so that's your what your median is, and your operation is just pick a range, replace that, delete all elements in that range, and replace it with the median. So this is the operation. This is the problem. I hope the problem is clear. So we can move to the solution now. So length to median is min value, and yeah, this observation would be important for this, that for a length of 2, as you have written, the median is the smaller value, and for a length greater than equal to 3, we can check second high element of length. So yes. So okay, basically, okay, I'll come to that thing. So now, for what you need to do, you are given an array. Okay, let's pick 1, 2, 3 only. Okay, let's pick 1, 2, 3. Okay, just check. First, check whether we can reduce this array to 1. Then check whether we can reduce this to, whether we can reduce this to 3. Okay, what if we want to reduce this to 1? How can we do that? Okay, the first thing is, if we can calculate the median of the whole array. Let's say I perform the operation directly on the whole array. L equal to 1, R equal to N, I performed on the whole array. What median would I get? The median of the whole array. So I would reduce this to one element directly, which is the median. For this case, the median of this is 2. Okay. So in one operation, I would reduce it to 2. So for 2, my answer would be yes. That I can purely say. That I can just apply the operation on full array, reduce it to 2. So 2 I can always make. So whatever the median of the array is, all elements equal to median, answer for them would be 1. Okay. Now what about others? Let's see for this one, what we can do. Okay, for this one, um, we want to reduce this whole array to 1. Okay, let's say if we pick all 3 elements, we would get 2. So we would never pick all 3 elements. Then what we can do? We can, if we pick any sub array of size 1, that would not make any difference. So if you just pick this, median is this, so no deletion, nothing happens. So we would always pick a range greater than 1. So greater than 1, what ranges can we pick? We can pick 2, 3. Here we can only pick 2 and 3. So let's see, for if you pick a range of 3, we are getting 2. So that's not valid. So only options we are left with, pick this range or pick this range. Okay, so now let's see what happens if you pick this range. Among 1, 2, my median would be 1. Among 1, 2, my median is 1. I replace 1. So my array is reduced to 1, 3. Okay. Now, then I only option is apply operation on this. Array is reduced to 1. Job done. Okay. Other way around was pick these two. Okay. Had we picked these two initially, then median of 2 and 3 is 2, 1, 2. Median of these two would be 1. Still we could have. So in both ways we can get 1. So 1 is satisfied for sure, 2 was satisfied. Let's say can we do 3? Now to do a 3, make this, reduce this array to a single element having value 3. So first thing, if we apply on whole, you would get 2. So not valid. So let's try this thing first. Okay, only options are apply operation on this or this. So let's first apply on this. After applying on this, we got this. Only way was apply on this and get a 1. So here you are getting 1. Other way was apply on this and get this thing. So here only you are removing this 3. So whatever you do, you can never reduce this array to a single 3. You can never reduce this array to this thing. So answer for this would be no. So you would return 1, 1, 0. Okay. Answer for the first index is 1, second index is 2, third index. This would be your answer. Okay. You can just look at the answer of this test case was 1, 1, 0. Okay. So I hope the problem is now clear what we need to do. So how can we do this? Okay. The first intuition that you get is, okay, I like tried many things in that. So I won't go too much what I have tried, but this one thing was at a good observation, which would help eventually. So, like as someone had pointed out in the chat also, that if we have if you select a range of two elements, let's say I'm selecting 1 and 2, then definitely for any range of two elements, the minimum of the two elements would be my median. Because for two elements, when we sort it, both are the middle elements and the left one is my answer. That's what the definition of median is. So for two elements, I can always have one as the median, so I can remove this two. So whenever we have two consecutive elements, one is greater than the other. So if we have some x and y such that y is greater than x, then by applying an operation on this, we can remove this y. And if we have x and y and x is greater than y, then by applying in this operation, we can remove x. Okay, let's say we had a z here, a x here, y here, z here, and y was greater than x, z was also greater than x. So first we applied operation on this, removed x. Then we applied operation on this, removed z. We got x. So if if we are looking for the smallest element, let's say we are at the smallest element, that can always be made as a last element. Whatever it has to its adjacent, just apply an operation with that, apply an operation with that, just remove all the elements adjacent to it by always applying an operation of size 2. Then you can always get an x in the end. So for the smallest element in your array, the answer is always yes. Now, what about the second smallest element? So let's say you had 1, 2, 3, 4, 5. Okay. What about the one? We are saying definitely it would be a yes. So we can just take this two. Okay, what we can do for one, take this two, remove this two. Then take this, remove this. Take this, remove this. Take this, remove this. Okay. Had we had one year, so had we had like this 1 year and 3 years. So I would say for this one, answer would be one because take these two, remove this. 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 So we can always get a one. So smallest element, we can always make it. Okay. So here, this was the smallest element, we can always make it. Let's see for the second smallest. 2 was the second smallest. Now the only problem is whatever values are greater than 2, you can, if they are adjacent to 2, you can just remove them. This 3 was greater, it was adjacent to 2, you remove them. But once you remove this 3, you got stuck here. Adjacent to 2 was 1. But if you apply a pressure on this 2, the 2 would get removed. So, so a little problem here. So what you can do is, okay, so what I thought after this is, the first thing was if you apply operation on the whole array, the median of the whole array, it was 3 there, so you would get that. So for any element, okay, so the basic thing was for any element, if you want that to be your final element, then your final operation in the final operation, that should be your median. So how can you make, so if you want to make 2 as your final element, you have to just determine how can you create such an array where 2 is the median. If you can reduce this array to such an array where 2 is the median, then after the next operation on that full array, you can make it 2. So your aim is reduce this array to an array where 2 is the median. Okay. Now, how can 2 become the median? What's the condition for median? Condition for median for any element to be a median is simply just count the number of elements smaller than x. Okay, just count number of elements less than x. Okay, let's say this is c1. Then count the number of elements greater than x. Okay, let's say this is c2. Now, if I would say x is the median, if c1 is equal to c2, for the odd case when x is then number of to the left and right both would be same, so c1 should be equal to c2. And if it is an even case, so greater elements would be just one more. Okay, so the greater would C2 would be equal to C1 plus 1. So if either of these two conditions are satisfied, then we can say X is the median. Okay, that's the first thing. Now, how can you? So if you, let's say, sorted this array, so whatever the middle element that you got, that for that your answer is yes. Now let's say the element just before the middle element. For that, how many elements are greater? So this elements greater than that, this C2 would become more and this C2 would be less. So you want to reduce this C2. If you can reduce this C2, then you can maybe make C1 and C2 equal or C2 equal to. You can satisfy any one of these conditions by reducing this C2. So all the elements less than median, for them you need to reduce C2. What is C2? The greater elements. Now how can you reduce C2? Just go to the maximum element, and let's say the maximum element in the array is at some position here. It is mx, it is the maximum element. Just apply this operation to any of its adjacent element, it would get removed, because if you apply an operation on two elements, the greater gets removed. So you can always remove the maximum element and reduce C2 by 1. Then again, whatever is now the new maximum, again remove it, reduce C2 by 1 again. So for all the elements less than median, you can always make them your median by just removing the maximum elements one by one. So for if you have an array, then for all elements less than equal to median of the array, your answer would be 1. That yes, you can make it. Okay, that's the first thing, first observation. Okay, that for all the elements that are less than equal to median of the complete array, your answer would be 1. Okay, now what about the elements greater than median? That was the main complex part of this problem. Okay, let's try to think. So what would happen for elements greater? Okay, so you had C1, C2. For elements greater than median, this number of count of elements less than x would become more and greater than x would become less. Okay, so you actually need to reduce this to make them equal. Okay, so you need to reduce the smaller elements. How can you remove smaller elements so that you can make these two equal, or just this thing? Okay, so how can you reduce smaller elements? For reducing the bigger element was easy. Just make an operation of size 2 with any of its adjacent element, this would get removed. But removing smaller element is a bit difficult. So let's say, okay, the first thing is, now the value of the element, you can say, does not matter, only greater or smaller matter for a particular fixed I. So what I'm trying to say is, let's say you have this array. Okay, let's say I'm indexing it 1, 2, 3, 4, 5. Let's say the median of the array is somewhat 4, and okay, whatever the median is, we are having a x at this. Okay, and this x is greater than the median. Okay, that's the thing. You have a x at this index which is greater than median. Now what you can do, just look at all the other values and just say who are greater, who are smaller. Okay, if this x, who are greater than x and who are smaller than x, that's what you need to see. Not, you don't need to compare with median, now with x, because you want to have number of elements less than x and number of elements greater than x. The count of those should become either equal or C2 equal to C1 plus 1. So here, as you saw, since x was greater than median, the count of elements less than x would have increased. So now I'm just telling the smaller elements with S, greater elements with G. Okay. So let's say this is a smaller element, this is a greater, this is also greater, these are smaller. Okay, so we have three smaller elements and two greater elements. Yeah. So this is okay. We have more smaller elements, less greater elements. That would happen for X greater than median. Now, what you need to do is you need to reduce these smaller elements. Here you have three smaller elements and two greater elements. You need to reduce this. If you can make this 3 to 2, you are done. You can just uh, uh, make this X as a median. So when can we do this? If you look, so first thing is, now we would always apply operations on length 2. Why? Because if we are, let's say, applying on length 3, just take any length 3, whatever be its median. If you have SGG, it means these are greater, these are smaller. So if you arrange them in ascending order, it would be SGG. So this G would remain and S and G would get removed. Okay, so whenever it's more than greater than equal to three elements, one of the middle would get removed. Okay, if the middle removed is G, then here and here. So what basically I mean, if this middle would remain, remaining would get removed. So if you are performing on this, one S would be removed, one G would be removed. Okay. So if you are reducing both the count of S and G by one, you are not making any effect. You want to equalize them, you only want to reduce S, not G. Like if you are reducing G, then reduce S more, then only you would get any benefit. But if you are reducing them equally, no benefit. But if you had three G's, let's say, uh, four G's, okay, this would become median. You would remove three greater elements, one smaller element. Okay. So here more greater elements you are removing, that's not okay. If you had three smaller elements and two greater elements, you would take this as remove two smaller, two greater. So no benefit. But if you had four smaller and one greater, you can keep this, remove three smaller and one greater. That would be beneficial. But if you are applying on these five values where there was four of them are S, it means you would have some consecutive S. Whenever you have two consecutive S, you can apply operation on this and remove this to a single S. That also you can do. So instead of doing like this, apply and remove, reduce it to a single S. SSS, apply, reduce to single S. SS, reduce to single S. You would be reduced to a single S. If you have some consecutive S, you can reduce all of them to a single S. That's what you can do by using operations of size 2 only. Using bigger operations, you maybe can do the same thing. But if you're doing the same thing, then why complicate the situation? Do it with a size of 2. It would never happen that you can do anything with a subarray of length greater than 2. Okay, if you cannot do anything with a length greater than 2, which you can't do with a length 2. Okay, I'm talking about only profit case where we are reducing more smallers. Okay, you can maybe remove more greaters, but that's not beneficial. You want to remove more smaller elements. So it would never happen that with a size greater than 2, you are removing more smaller elements. Uh, if you are, then you can do the same thing with a size of 2. So I am now considering only operations of size 2. So if you have operations of only size 2, I hope you are understanding the feeling. Okay, now like I'll come to the thing. Okay, so if you have operations of size 2, then what all can we remove? So what all cases can we have for size 2? SG, SS, GG, GS. Only these cases like we can have. So if you apply on this, you are removing the smaller. That's not beneficial. If you apply on this, you are removing one of the smaller into a single form. So that is beneficial. If you apply on this, you are removing a greater element, not beneficial. If you are applying on this, you are removing the smaller element, not beneficial. So the only benefit you can get is when you have two consecutive s, two consecutive elements which are smaller than x. So here you had two consecutive smaller than s, you can reduce to a single s. So if you have some s, whatever consecutive pair of s you can have, you can reduce all to a single s. So basically, after doing these reductions, once you have done these reductions, you cannot do any more reductions. Once you have something like this, a greater, greater, smaller, greater, smaller, greater, smaller, greater, 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 smaller, smaller. Let's say you have something like this. Okay. In between there is a x, then again smaller, greater, greater. Okay. Let's say you have something like this. Okay. If you have something like this, after this you cannot reduce more. What, you don't have any consecutive s, you can look at this. If you don't have any consecutive s, you cannot reduce this more. So first thing you do, whatever consecutive s you have, reduce those, that to a single s, and then whatever you get, just count the number of s and number of g. So number of s is your c1, number of g is your c2. If that satisfies one of these conditions, then you can say yes, you can do. Otherwise, you would say no. You can, then you cannot do, but not this condition. Maybe you can reduce more, and then reduce as, let's say the count of C1 is here only. You can see 1, 2, 3, 4, 5, 6. Okay, the number of S is 6, and number of G is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So if you say check like this, C1 equal to C2, and C1 equal to whatever C2 plus 1, or C1 plus 1, C1 plus 1. Okay. If you are checking this thing, it is not satisfying this. But you can make it satisfy this if this C2 is greater than C1. Then you can reduce the greater elements also. You can always reduce greater elements. Just pick with any smaller, pick with any two consecutive, whatever you do, you can always reduce greater elements. So if you get the count of smaller as less than equal to C2, okay, then you can say it is satisfied. Or C1 plus 1 equal to C2 for that. So C1 plus 1, you can say, if this is less than equal to C2, then you can say it is satisfied. So basically, that's what you need to do. Reduce all the smallers to a single s, then count the number of s and g. If number of s plus 1 is less than equal to g, then a 1, otherwise a no. Now, how can you do this optimally? That's another problem. If you do for each x, okay, okay, I hope till this it's clear. Now, if you do till each, for each x, once you set this x, now if you go to this index, our x would be different. So smaller and greater would be different. For a different value, there would be different smallers and different greaters. So you, for each x, if you are doing it, it would go off n square. So it won't be possible. So how can you do it optimally? Okay. So for that, a simple thing is just go from smallest to greatest. And while going from smallest to greatest, okay, just insert the, whenever you go to some I, okay, first check the conditions. Okay, after that, maintain a set of indexes, storing the indexes of S. So whenever you go, if you are going in ascending order, so if you are going in ascending order, you are going for with a value of 1, then a value of 3, then a value of 5. So when you were at 1, so whatever indexes of 1 you inserted in your set, so that was smaller for this 3. Whatever this you inserted, whole for 1 and 3, both were smaller for 5. So you can just keep, if you go in this ascending order, you can keep inserting the indexes of these values into your set, which was represent the set of smaller elements. And then through that set, how can you compute number of smaller elements in the reduced form? Okay. So if you have small, small, great, small, x, small, greater, smaller, smaller. Let's say you have this. So in your set, you would store these indexes 0, 1, 2, 3, 4, 5, 6, 7. In your set, you would store the indexes of S. You would have the indexes of S. In your set, you would have 0, 1, 3, 5, 7, 8. For this particular case, you would have these indexes. So by looking at these indexes, can you compute the optimized form? What was optimized form? Reduce these two S to a single S. This S is alone, this is alone. Reduce these to a single S. Their optimized was S, G, S, X, S, G, S. This was your after performing operations, the reduced, whatever you can reduce, the lowest form. So look by looking at this set, can you do that? Yes. What you can do, whenever you have two consecutive elements in your set, take a counter variable, let's say C, add a plus 1 to that whenever the element, the index you inserted, let's say you had this in your set, and after a point you inserted index 1 into your set, you would check I minus 1 and I plus 1 whether they are in the set. When you inserted 1, you would check, is 0 in my set? Yes, do a C plus plus. Is 2 in my set? If yes, do again a C plus plus. So if we had SSS 1, 0, 1, 2, if 1 is inserted, it's reducing the number of count of S by 2. This whole 3 would be reduced to a single S. So this C would store the number of reductions in my S. Okay. So what would be the number of S? So number of S would be size of my set minus C. Okay. I hope that is clear. In the set, you are storing the indexes of your smaller elements. So the size of that is the number of smaller elements originally. But if you are reducing in your C, you are storing number of consecutive elements in this. If you subtract the consecutive elements from the total number of elements, you would get number of S in the reduced form. So once you computed this, let's say this is C1. Now what would be your C2? C2 would be, what's the reduced size? Reduced size of this original size minus C. So your C2 is just n minus C and minus 1 because your X is, you won't count X in your C2. You're only counting greater elements. So this would be the number of greater elements. This is C2, this is C1. Check the condition and do a 1 or 0, yes or no. Okay, I hope the logic is clear. One more small thing was there, that you may have equal elements also here. Okay, one thing that we maybe not covered, you may also have one. Okay, and how you are iterating also, that also. Okay, so you may have 1 2 5 4 4. Okay, like this you may have your array. There are two ones. So what the thing is, if you're calculating for this one, you can consider this one as smaller also, greater also. Okay, because in your median you would have one, either this is at the like middle position of this, both would give one as your answer. So when you're considering for a value one, so instead of storing uh, like this, like indexes, you would store a map. Map of one would represent the indexes of one. That's what you would store. A map of int comma vector. You are storing a map of int comma vector. So map of one will have a vector of indices where one occurs. So here it would have 0 comma 1. Okay, and then map of 2, the indices where 2 occurs, it is 2. Map of 5, okay, map of 4 first, 4 and 5, it would be in sorted order. A map is, we are using a sorted map, so you also get the benefit You can iterate through this map in sorted order. Okay. So first, from the array, make a map like this, a map of vectors storing the indices where particular value occurs. Then you would iterate through the map. First, you went to this one value. You had 0 and 1 indices, but before that, before inserting this to your set, you checked. So now these are not inserted to your set. That means the elements, okay. So if you have two ones, so you can consider, if you are checking for this one, you can consider this as greater also, smaller also. What would be better to consider? You want to max have more greater, so it would be better to consider it greater only. Okay. So if you have multiple ones, consider the other ones as greater. So that would be beneficial because you want to have more greater elements. Okay, so that's the small thing, that consider them as greater. So you would not add anything to your set because you don't get any greater element here. So when you go to this, your set is an empty set. You checked for the condition. So your C set is empty, C is 0. You checked, you calculated C1 as size of set plus C. So 0 plus 0 was 0. You calculated C2 as n minus C, uh, n minus C minus 1. Okay. So here it was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it was 6 minus 0 minus 1, which was 5. So obviously here you didn't have C1. Your condition was what? That C1 plus 1 should be less than equal to C2. So yeah, C1 plus 1 was less than equal to C2, which is satisfied, you would give a 1. Obviously, for smaller values, before median, you would always get a 1. Okay, so here you would get a 1, but where would you write that 1? You would write that 1 to all the indexes of 1. So again, you would iterate through the indexes of 1 and write a 1 in your string. Okay, in your answer string. And other thing you would do, you would insert this 0 and 1 to your set. Along with inserting, after each insertion, you would check whether I minus 1 occurs in my set, then do a C++. If I plus 1 occurs in my set, do a C++. So three things you are always doing for each element. Insert it, check if I minus 1 is in the set, do C++, check if I plus 1 is in the set, do C++. You are doing three things for every uh, index. Okay, do this for this, for this. So, so that's the overall thing you are doing in each iteration. I hope it is clear, so we can look at the code now. Okay. Okay, so we initialized our answer string with of n size with all ones. So we initialized that all are possible. Whenever we get a 0 that it is not possible, we'll replace it with 0. Okay, that's this is all input. Okay, now I created this map of int comma vector int. So map of ai dot pushback I. So in this way, for each value, ai is my value. For that, I'm inserting the index into the vector of that map. Okay, so this way I created the map. Then I took my set and my C. So this is my set storing the smaller values. This is my C storing the count of consecutive elements in my set. Now I would go to each element of my map. Then my P dot second is my vector. P dot first is my value. Okay. So then I would check. This is my C1 set dot size minus C. Is this greater than equal to, okay, uh, like what I condition, what the condition I had written, you could do that, or what I did. Okay, sorry, one thing I missed here. The count of C2 was not this. You had to do minus C1 also here. This thing was the count of, this was the size of my reduced array. From that, when you reduce the smaller elements, you would get the number of greater elements. Okay. So you would check, this would be a C2 minus C1. Okay. So One way is just write C1 equal to set dot size minus C, and then C2 equal to n minus C minus 1 minus C1. Okay, compute this C1, C2, then check this condition. What was it? That whether C1 plus 1 is less than equal to C2. I think this was the condition. Yeah, C1 plus 1 is less than equal to C2. Okay, so one way is compute C1, C2, and then write this if. If this is satisfied, it's a yes. Otherwise, if this is for no, like I'm computing, if this is greater, then it's a no. Just replace your string with a no. Okay, so that's one way from my explanation. And in my code, I had computed it little differently. If you want, you can understand that also. This is the number of elements in my reduced set. Okay, this is basically C1 plus C2. And I'm doing by 2 here. So if C1 is greater than half of C1 plus C2, so basically mathematically both the things are same what I wrote in my there in the explanation and this thing. Okay. So this would also satisfy. So this was C1, the number of smaller elements. If number of smaller elements are greater than equal to total number of smaller plus greater by 2, then it means we have smaller in majority. And if we have smaller in majority, we would say SI is 0 by going to each index of my p dot second is the vector I have for this, for the particular value. Okay, I'm iterating through the map. For the current value of map, the p dot second is the value vector. Okay, so for each index of that vector, I'm doing SI equal to 0. So that's the first thing. And then I have to update my set. So I'm going to each index of p dot second, each index of the vector, insert that to the set, check if I minus 1 is there in the set. If it's there in the set, then do a C++. If I plus 1 is there in the set, do a C++ again. So this way you would just compute your answer string, which is S, you can just print it. Okay. So like in here in else I didn't wrote SI equal to 1 because I had already initialized SI to 1. So whenever we got a node, we just replace that node. Okay, so I hope it is clear now. Like if you look at the time complexity in the map, I'm inserting every element. I'm going to the value of map and inserting to its vector. So it's a log n, it would take log n time for each insertion. That I'm doing n times. So this whole thing is O of n log n. Okay. So, and the size, maximum size of my map would be n because maximum we are inserting n elements into the set at max. Okay, into the vector. So we are inserting at max n elements. So here when we are iterating to p and then iterating to p dot second, so this thing or this thing, in total it would be executed n times. So in total n times we are inserting to the set. This is log n operation. This is also log n. So 3 log n operations are there. This is done n times. And this O of 1 operation is done n times. Overall time complexity for this would be O of n log n. Okay. N log n here and 3 times n log n here. So total 4 times n log n it is. It's a heavy n log n. If you see, like I had actually got a TLE first in this problem. I had like written this int x equal to p dot first, just that, and I was getting TLE, and then I saw that this x is not used. This is not required. I just removed that, and I got accepted. Like it was a little crazy thing, like why it was giving TLE here, but yeah, it is n log n, but a heavy n log n with a greater constant. So you need to write a little in an optimized way as much as you can to get accepted here. Okay, so I hope the problem is clear now. Okay, so is there any doubts in this? So we can, yeah, it was heavy, so we can now end the session.
Yeah.
Thank you very much.